thank you everyone for joining today. So my talk today is going to be about the STM functionality in ZIO. And we're first going to motivate a little bit by just talking about like concurrency and why is concurrency hard and why do we need something else? Why do we need some other tool? And then we're going to go from there to talking about just like what is STM other than this like new set of letters that we need to learn. What motivates it? What is it? What's this overall approach and what does it bring us? And then finally, we're going to talk about ZIO's implementation of STM, what the design philosophy and motivations were behind that, and what it brings to the table. So to start off, I'd like to motivate us with what I'll call a simple problem here, which is implementing this memoize operator that is basically going to return a memoized version of some effectual function here. So we can imagine this maybe opens some resource, maybe it creates some kind of tenancy, and it does it based on some maybe tenant ID. And our boss comes to us and says, well, we got a problem. People keep calling this method and they kind of recreate the same tenancy over and over again. And it's expensive to do this. And we got to like stop this. We got to have some way of creating one version of this method that if the thing's already been created, then we just grab it and we give it back to them. If it hasn't been created, then well, we go and create it. And then that version we give to anyone else who's interested in that. And this new function we return here may be called by multiple people from multiple processes, multiple parts of our program. So this has got to be concurrent safe. And so the traditional solution to a problem like this would say, well, we should start out by defining some data type that's going to represent all the possible states that are relevant to our system. And so I think here we could convince ourselves pretty easily that this map from A to promise EB is sufficient to represent all the states of our system. And we could think of, for any value A we look up in this map, we're either going to get a none, which means we haven't seen this value before, or we're going to get a sum with a promise. And then that promise in turn can either be incomplete, of someone's in the process of computing it. It can be completed with a successful value, or it can be completed with a failure. And we can the same possibilities for any value. So this can represent all the possible states that our system can have. And then the next thing we do in this approach is we'd say, okay, well, we should take that state and we should put it inside one of these ref things, which is the version in ZIO of a atomic reference if you were working in Java, and basically lets us manage mutable state in a concurrent safe and a declarative way. And once we wrap our state up in that ref, then any operations we want to do, we should always do in terms of this modify operator on the ref. And every time we call modify, we should return two things. We should return a new state, that is the updated state based on whatever operator got called here, and we should return some action that we want to run based on this state. And then this flatten operator here is going to make sure we actually run this effect that we're returning here. And so in this case, we basically got two possibilities of like, someone's asking us for an A, we're going to look in the map and we're going to see if we've got an A. And the easy case is, well, there's already a promise in the map, which here means someone's already computing the value of this thing. And this promise is either just done and the value's there for us, or someone else is in the process of computing this F for that A and is going to update the promise with that result. And so here it's really simple. We don't need to update the state at all because this is already in the map, and at least in this simple case, this state transition is kind of a one-way thing of it's either not in the map, or once it's in the map, it's just in the map forever. And then we can just wait for the promise. And in the slightly more complicated case is where a value isn't in the map yet. And so that means we're the first ones to see this value, and we need to take responsibility for computing that value and for updating that promise with it. And so you can see here, we had to make a couple of changes here. So one is we had to add creating the promise outside of modifying this ref. Because when we're doing the modification, we can return an effect we want to run, but we can't actually perform effects within the modification, the updating of the state. So to have this promise even put in the map, we have to create the promise up front, which we're not going to use at all if it's already in the map, but if there wasn't one before, then we'll have this promise. And so in this case, we've got to update the state by putting in this new binding in the map that says, well, now if you're interested in this particular A value, here's the promise you wait for. And then we're the ones who are responsible for completing the promise. So we call that F function with the A input. And then we use this into promise operator, which is going to take the result of this F of A, whatever it is, whether it's a success or a failure or an interruption, and it's going to make sure that gets sent to this promise here. And then we'll just wait for that promise. So at this point, we can kind of say, okay, well, what's good and bad about this solution? How do we evaluate this kind of approach? And there's some definite good things we can say about this. We correctly implemented a concurrent safe solution to our problem. We did it in relatively few lines of code. There are probably less than 10 lines of code there, depending on how you count braces. And we did it in a way that had all the nice things we expect from a framework like ZIO. It was not blocking, it handled interruption, it handled all of those things that we just kind of expect from a framework like ZIO. So great. But I'm going to try to convince you that there are actually some things that are not so great about that solution. And they fall into, I'll call them 3 categories. So 1, just it being not that simple. 2, and related to that, it being prone to bugs. And 3, some issues with how this scales for us. So on the first point, I think you can probably see from those code examples before that it was not the simplest thing. We had to use this modify, and then we had to use this flatten operator, and we kind of had to think about like this modify is returning an effect as a value that then we were going to need to run. And that just requires a little bit of thinking about how to do this that probably, if I didn't tell you specifically, like, this is how you should do this thing, or you kind of heard some other person or read something that said something similar, then this probably isn't necessarily what you would come up with yourself. We had to use this into promise operator, which is a little bit of a specialized operator. And again, something like I think you probably have to like know a little bit like, oh, this is interruption is an issue here, and I need to make sure I really propagate all the results of this computation into this promise to like know that like that's the operator that you should use. And also we had to just use multiple concurrent data types, even for this problem that was pretty simple, that I think is probably like the lower bound of like a problem I could present in a talk like this that you wouldn't just kind of say was like trivial. I had to use both a ref and a promise. And that's almost always going to be the case, because essentially anytime I have some kind of state that changes, I need a ref. And anytime I want to be able to wait for some condition to occur, I need a promise. And so I'm always going to need both of those. And this case, in a way, it was very simple because it was this one-way state transition of like, it's either not done or it's done, which is the same way the promise works. If it's kind of like a box that's either empty or full with a value. But if I have anything that has more complex transitions that like can be empty and then full again and then empty again, and I want to be able to wait for it both ways, but I'm just going to have more and more nested refs and promises, and it's going to get a little bit complicated. The second thing is this approach I walk through is kind of steering us like between Scylla and Charybdis, between a bunch of different like bugs that we can create. Essentially anything I do to modify that state that's not part of that like one modify operator is pretty likely introducing a bug. If I do like a get and then I do a set separately, if I do some other update somewhere, it's very easy for me to introduce a concurrency bug here. And I also have to be very careful about when effects are evaluated. Like we had this idea of, well, I'm returning an effect and then I'm evaluating later with the flatten, but then we saw I had to create a promise up front because I wanted to have that when I updated the state. So there's a decent amount of thinking that we can have to do about that. And then we saw that issue of having to explicitly wait for these expected conditions. The final thing that I think is maybe the most important conceptually is just, in a way, this doesn't really scale for us. This whole approach amounts to taking all the state that's relevant for whatever we're doing and putting into this one ref, which is essentially creating a global state for whatever this thing is that we're doing. And sometimes that's fine. Like I think in this case, this little memorize operator, it's probably fine. It's relatively small, but let's just think about like the trade-offs and the issues involved there. Because this ref thing, like it can seem maybe like a little bit just like, you know, maybe if we haven't thought about it, it's just this thing that like, okay, it's manage a state, it's concurrent safe. We don't really think about it anymore. But the ref is just a wrapper for this Java util concurrent atomic reference here. And the way that the modify operator works is it just does this loop where it basically just retries if there's any other change to the state. So it just gets the original state, then it runs this update function, and then it tries to set the state. And if it finds when it does that the state got modified by someone else, then it just retries the whole thing. And so when we create this like bigger state, what it means is that we have more and more cases where maybe someone else is updating some other part of that state and is forcing us to retry. So we can imagine even this really simple example where we have this like map, theoretically, we kind of would like to be able to say, well, if we're updating one key in the map, that shouldn't make someone else retry when they're updating another key because we're not updating conflicting pieces of information within the state. But that's not the way that ref works. Like ref says, hey, if you made any changes to the state, then we got to retry the whole thing. And so the bigger that state gets, the more often we're likely to have to do that. So, and this just kind of walks through those points of we have to retry. This kind of traditional approach is just solving the problem of concurrent state by really having one state for at least this part of the program that we're working with. And if the state's small like this, then maybe that's not a big deal, but we can imagine if the state has a lot more components to it, the fact that we have to put them all into one ref to work with this gets a little bit problematic. So what does STM bring to the table here? What is it at all, and how does it help us address this? And to motivate that, I think it's helpful to think about what's the root cause of the problem that we were running into in the first section. And it's basically this idea that these atomic operators don't compose with each other. So here I've created a simple test where we're making one of these ref things, and then I've defined this update operator, and all it's going to do is it's going to get the value of the ref, and then it's going to set it to one more than whatever the value was what it got. And then I'm just going to call the ZIO collect all par operator on this chunk that has 10,000 of these updates. And so naively, we might think, okay, well, update adds one each time. I'm doing it 10,000 times. I'll do a little bit of math. 10,000 times one is 10,000. So when I'm done with this, I should get 10,000 when I get this ref here. But this test is actually going to fail non-deterministically. And with this many updates, I think almost always when we actually run it, it's going to fail. And the issue is that we can have these different fibers that are running concurrently with each other, stepping on each other. And so a simple example would be, say we have two fibers that are going at the same time, both of them call ref.get, and so both of them read a value of, say, 0. And so both of them say, okay, well, 0 plus 1 is 1. So both of them set it to 1. And now we've had two updates, but our final value is 1. So we've already gone off the rails here. And so what we learn as we do a little bit more with these data types is that when you're working with this ref, it's actually only that modify operator and operators that are defined in terms of it that are atomic. We can't do a separate get and a set. We have to do a modifier. We have to do this built-in update operator here that's defined in terms of that built-in modify operator that does that compare and swap loop here. And so in this example, it's exactly the same as the one on the previous page, except I replaced that update that was the separate get and then set with just this ref.update. And now this is going to do exactly what we expect of. Now it's going to always give us this value of 10,000. But the problem is there's no modify operator for more than one ref. So if I've just got a single ref, then I can use modify to do these updates atomically. But if I have two different refs, there's no way I can do that. And what we realize when we think about it a little bit is it's actually a pretty fundamental limitation with this approach, because we saw that like that ZIO ref data type and similar ones in other frameworks aren't doing anything that amazing themselves. They're basically wrapping and delegating to this Java atomic reference. And they're working with this compare and set primitive that it has. And compare and set, in turn, is implemented typically in terms of much lower level machine instructions that actually support atomically setting a memory location if it has an expected value. And those instructions only exist on major architectures for one memory location. There's no way to do it for two memory locations, or much less arbitrarily many memory locations. So since we've built our whole approach of doing this on these like primitive operations, and this primitive operation to do what we need just doesn't exist, we're kind of SOL with this approach if we actually need to modify more than one of these refs. And so one way to think about like what that traditional solution was that I walked us through at the beginning of this talk is it's essentially saying, well, okay, we can approach this by saying, if we can't atomically update multiple pieces of state, then we can just never allow multiple pieces of state to exist when we care about some consistency between them. And so that leads us immediately to, okay, we need to represent all the information that's potentially relevant to what we're doing as part of one piece of state that is part of one ref. And then we never ever have the problem of having to update multiple refs, because we only have one ref that describes the state that's relevant to what we're doing. So that's fine. We can use that for a lot of things, and we saw like that let us solve our memoized problem. But how would we go beyond this? How would we go beyond just having to put everything into one of these refs? And that's essentially what software transactional memory, that's the STM of the STM, so software transactional memory. And in a way, it doesn't necessarily matter that much what the words are, but just that's kind of the label for this thing. That's what software transactional memory tries to do. And it's essentially asking the question of, what would it take for us to build our own infrastructure for doing these atomic updates? So we saw that previously we were working with this infrastructure that was kind of leveraging this existing infrastructure of like going to Java util concurrent, going to the atomic reference, going to their compare and set, going to machine level instructions that bake that. And we kind of saw we got to a end of the line there. And so what would it take for us, instead of relying on other people's infrastructure that maybe doesn't have everything we want, what would it take for us to build our own infrastructure in code to support this in a composable way? And it turns out we actually only really need a few concepts. And so the idea here is that we can build up what we could call a transaction that's a description of all the updates that we would like to make. So at this point, we haven't actually made these updates, but we've got like a data structure, a little bit like ZIO is a description, but this is a description that says like, hey, I would like to update reference A to B2, and I'd like to update reference B to B46. And at that point, I haven't actually updated those references. I've just got this transaction that says I would like to do this. Second thing that we're going to need is we're going to need what's called a journal that's going to keep track of all of the variables we've read from. So maybe in the process of saying we want to update A and B, we've read from C, D, and E. And so the journal is going to keep track of all the variables that we've read from along the way, as well as what their values were when we read from them. And then what we're going to do is when we've got this transaction and we want to actually commit it, we want to take it from being a description to actually setting the values to the values that the transaction says it wants to set them to, we're going to go back through that journal and we're going to check each of those variables that we included anywhere in our transaction, and we're going to see if they've been changed since we looked at them. And if they have, we're going to retry. We're going to essentially do the same thing that that atomic reference was doing. And if not, then we'll update the variables. But because we've got this list of everything we're doing, we're going to be able to potentially look at more than one variable or more than one change to a variable. And so what this lets us do is have these STM operators compose in that way that we saw that the normal atomic operators didn't compose. So here's the exact same example that I showed at the beginning of this section, except I've put it into this STM world, which basically just means I put a T in front of it. The T stands for transactional. So this is a transactional reference. It's just like a ref in terms of most of the operators on it, except it's able to do these STM operations. And so really the only difference we'll see here is I just have this additional operator called commit that says, okay, we'll actually take that thing and make those updates. And that turns it from being a STM value to being a ZIO value. So here I'm just going to make this ref, and I don't need to worry about concurrency, I'm just making it. So I'm just going to commit that. And then I'm going to define this update operation myself. And here I'm just going to do it in like the most simple, intuitive way I can think of. I'm just going to get the value, and then once I get the value, I'm just going to set it to one more than that. I'm not going to think about any special operating to do. And I'm going to commit this thing. And then I'm going to do exactly the same thing I did before. I'm going to take that update, this ZIO operator right now, the ZIO workflow, and I'm going to run it 10,000 times. And this time this test is going to pass. This is always going to be 10,000 because the fact that I did these operators within one block that I committed means that as far as the rest of the world can see, these are always going to occur as if they were one atomic operation. And in this case, I could have done this particular atomic operation like with a normal ref with update, but this STM transaction can potentially be as large as I want it to be. And it doesn't even have to be limited to one variable. This concept, right, nothing of this logic of like the journal or checking the journal or keeping track of this transaction was limited to one variable. And so if I reference multiple variables, I can keep track of all of them in my journal. I can go back and check their values immediately before I commit this. I can retry it if I need to. And so this lets us solve that problem of being able to update multiple pieces of state, multiple references in a consistent atomic way here. And the guarantee this gives us is that no transaction that's based on an inconsistent state can ever be successfully committed. So again, internally, we may have to retry this, we may make one change and we may have to roll it back, but no one is ever going to be able to observe a situation where we successfully commit a transaction based on an inconsistent state. And there are a couple of really nice properties that are attached to this implementation. So we saw this idea that transactions based on inconsistent state can't be committed. Another really nice one is that these retries never happen by busy polling. So when we have to retry something, we're never just retrying again and again and again and again. But they only occur when one of the underlying transactional variables has changed. And that's both efficient for us, and we'll see in a sec actually lets us do some very cool things with that. And then the other thing about this is just like everything else in ZIO, waiting for a transactional variable never blocks a thread. So under the hood, if we have to retry, if we have to suspend waiting for something, all of that is implemented in a completely non-blocking way, using callbacks, using ZIO runtime under the hood, but we never have to deal with that at our level. So one of the really nice things about STM that goes back to that idea of retrying is it actually gives us a really nice alternative to working with promises. So we saw when we were doing the traditional approach that anytime we wanted to wait for an expected condition, we had to create a new promise and we had to wait for it and we had to deal with all of that infrastructure. And in STM, waiting is actually almost dead simple, almost trivially simple. And so like here, I've implemented this transactional promise. And it's a really simple representation here of it's just one of these references that's an option of an either EA. And so basically the none case here means it's not done yet. And the some case means it's done with either a left that has an error or a right that has a success. And here's what we need to do to wait for a value. All we do is we get the value of the ref. And then if it's got an either, if it's done with a value, then we can just return it. And if not, we just retry. And again, this retry is not going to busy poll. It's not going to do anything like that. It's just going to essentially record this somewhere as this is something we want to do. And when the value of this ref changes, then it's going to try to do this transaction again. And so this is what it means to wait for something in STM. And like, you don't need to implement this yourself because this is like just copied and pasted the implementation from ZIO STM. But you can see that relative to some other things that are very low level, you'd like, oh, I like never want to implement this. If you want to implement this yourself, you could implement it yourself very easily. It would be hard to implement this incorrectly, actually. So, okay, I've told you some of the good things about STM. What are some of the limitations we need to keep in mind? So the key idea here is we saw we need to retry these transactions, potentially an arbitrary number of times. Hopefully we won't actually retry them that many times, but definitely we may need to do them more than once. And so what that means is that we can't have arbitrary side effects within these STM transactions. So just like when we were updating the state in the original example and the state update was just adding a value to the map, we can just, if we need to, we can add a value to a map as many times as we want to. We need the thing we're doing in the STM transaction itself to not be doing side effects, to not be printing the console or call databases. It turns out that's actually not much of a limitation for us because even though we can't do those side effects within the STM transaction itself, we can use the STM transaction to decide what side effects we want to do immediately afterwards. I think that's one of the things that people most often don't appreciate about STM is like there's some of these examples of like, oh, well, we're going to do like dining philosopher's problem or something. And I mean, it's great to kind of show like the composition of these different pieces of state, but I think there's a risk that people kind of see it and they kind of take away, well, my problem does involve side effects. I am writing the databases and printing things and doing network calls and all these things. And so how is this relevant to me? And the answer is that you use the STM to update your state in a consistent way. And then based on that state you see, you decide what is the right network call you want to make. Do you want to create a new connection to the database or do you want to wait for an existing one? And so the two actually go hand in hand. If you really do need to do side effects within the transaction itself, there's something called the Saga pattern you can look at. There's actually a library called ZIO Saga that implements this. And the idea there is that you provide kind of your own user-specified way of what it means to roll something back. And then the framework will do something similar to what STM does to kind of undo that if necessary. But I would say the vast majority of cases, just the STM functionality will actually get you what you need. So, okay, that's STM overall. What's ZIO STM about and what does ZIO STM bring to the table? And to answer this, I think it's helpful to start by thinking about the design philosophy behind ZIO STM. And I'll describe this from my perspective. This functionality was originally developed by John. Another one of the ZIO contributors, Dayon, did a tremendous amount of work on that in both ZIO 1.0 and then completely redoing the runtime for ZIO 2.0 to make it more efficient. So I don't want to speak for them, but I'll give kind of my perspective on the design philosophy from the work I've done. And I think it starts with this idea that STM is probably one of the most distinctive contributions of functional programming to concurrency. And I'll talk a little bit more in a second about why I think that is. But that STM is dramatically underutilized. And that there's actually a set of reasons for this, primarily around ergonomics and performance, that keep people from taking advantage of STM, even though it's actually got a lot to offer them. And that STM implementations really have to address that if we want to change that underutilization. So let me unpack that a little bit. So first observation is this idea that STM is one of the most distinctive contributions of functional programming to concurrency. And that's not at all like touting like ZIO. I mean, STM didn't come from ZIO, didn't come from Scala, it actually originated in Haskell. But it really tackles one of the key issues in concurrency. If you go back to even some of the early talks like Marnodarsky did, when he was just like motivating the Scala language at the very beginning and like why this combination of like immutability and object orientation, the points he made was mutability plus concurrent state leads to programs that are hard to reason about. Because when you have those two things going on, you have all these possibilities, these inconsistent states being created of like, really your business logic is you can either have kind of state AA or BB, but now you have these different processes that one's modifying the first part and one's modifying the second part. And so now maybe someone's reading AB or BA. And what does that mean? What are they doing with it? Are they going off in some completely crazy direction based on that? And so there are a lot of different paradigms that have tried to address that over time. Like you can think about actors as a way of addressing that, of saying like, okay, let's get control of this like mutable concurrent state by putting each piece inside this actor and serializing updates of that state by saying the only way you can interact with it is you can pass these messages. And then the actor is going to, one at a time, process those messages. And it's internally is the only one who's really going to get to access that mutable state in there. But almost all of those solutions don't actually compose. Like you want to talk about like at a very high level, like architectural differences between like a functional programming versus an actor-based approach. Actor-based approach, great to like put your state in that one actor. What happens when like two actors need to modify state in a concurrent way? The answer is probably they need to be refactored to be one actor, which not the most composable thing. Versus functional programming, thanks to this idea of STM, has this like very straightforward solution to this that is composable and is implemented using a lot of these classic ideas of functional programming of we're building up this description of the transaction separate from actually executing it. And we're interpreting that and we're checking things as we go. We're taking advantage of the tools of functional programming to do this. So then second observation is, I think STM is dramatically underutilized. I think it's probably one of the most underutilized features in ZIO. And the basic pitch for STM is STM lets you trade off some performance relative to like a hand optimized concurrent data structure for dramatically higher developer productivity. When you use STM, essentially your problems of like concurrent state, the hard things about concurrency basically just go away for you. And so you can take almost any hard problem in concurrency and you can just do it with STM. And maybe it's not going to be as performant as if you went and you did it the lowest level way you could. But a lot of times that's not really going to matter for you. You're dealing with some connection pool and you need to have certain logic that you need to be consistent in the way you're like creating and shutting down and maintaining the size of this connection pool. But the time that it takes to actually like create or shut down these connections is orders of magnitude higher than the time it takes to update this state. So if you can trade off like the little updating part taking longer versus like your developers just being able to like immediately do this and like it being accessible to many more of your developers, you just immediately doing it, you not having bugs, you not having to open new GitHub issues because there was some bug and now you need to fix this and now you need to have new reviews for it. That's like a huge win in a lot of cases. And just from my own experience, like being on the ZIO Discord and answering questions, like I get questions about a lot of things. I don't get a lot of questions about STM. And I'd love to think that's just because everyone gets STM and it's like so self-explanatory, but I don't think that's the case. I think a lot of times just people aren't like using this piece of functionality. And I think in a lot of cases, they would really, really benefit from it. Of, you know, if you're doing anything with concurrency and like you don't feel like you're like the concurrency person of like everything I said at the beginning was like totally obvious and trivial to you, this is going to make your life like way easier. And you know, maybe some cases you're going to say, well, the performance does matter, and that's great. Like maybe you do this first, and then you open an issue of like, okay, now we need to do the more optimized implementation. But this is a huge tool you have in your toolkit that I think people are not taking advantage of. And so you can say, okay, well, if what you said is true, Adam, like, why is that? Why aren't people using this? And I think there are a couple of reasons for that. So one is this, what I call like the one more thing of just, it's one more thing of like, you already have to learn ZIO, you have to learn Z-manage, you have to learn streams, maybe learn these concurrent data structures. You're probably interested in a lot of other things aside from ZIO, maybe. You're not just all about ZIO. And so it's just like one more thing. And it's easy, like if it's not like very obvious to you how this is going to solve your problem, you're just like, hey, I need like a distributed message broker. And like, okay, like Kafka's like the thing for that. Then like it's easy to say, well, let me just like not do this thing. You just do something else. I think the second thing that has held STM back a lot historically is a lot of the implementations have had very poor ergonomics, I would say, where you had to do these like weird things where like it wasn't just like a class that had methods on it, but like there was some value and you had to like create the value and then you had to import that. And it was just like very weird and awkward. And some have also had prohibitive performance overhead, where I've talked to the senior engineers organizations and said, you know, I've tried this STM thing and it was just too slow for us and we had to revert. And there's always going to be some overhead of doing this STM, of keeping track of this like journal and stuff. And it's not going to be right for all cases, but if we can really address that performance issue, we can make it close and acceptable enough that that developer productivity trade-off makes sense in a lot more cases. So that's kind of what motivated ZIO STM, and I'm now going to walk you a little bit of what we've done to try to address that. And so I'll start with ergonomics, and essentially the idea here is to make STM as familiar as possible to what you already know, so that you don't really have to learn anything else, or you have to learn very little else. And so here's what this STM data type looks like. And you can see that it looks like ZIO. I mean, basically, if I take the ZIO if I take the IO of ZIO and I replace the IO with STM, these type signatures look exactly the same, right? It has the R, the E, and the A. It has flat map, it has map, it has succeed. It has basically all the constructors that we're used to with ZIO. And the only real exceptions are we don't have ones for importing side effects. So we don't have like there's like ZIO async. There's a lot of specific constructors for importing side effect in code. We don't have those because we said we can't do arbitrary side effects with an STM. And then there aren't concurrency operators in STM because you don't do concurrency within STM itself. You use STM to describe these transactions, then you may use those transactions concurrently. But basically, other than that, any operator that exists on ZIO also exists on STM. Same name, same type signature. The other side of that is there's very few actual new operators that you need to learn to use ZIO STM. So there's this atomically or commit, which we saw before, that takes your STM and it says, okay, take this block and atomically do it, and turns it from this STM kind of description of I'd like to do this transaction to a ZIO workflow of like, okay, we're going to actually do this thing. And then there's that retry one we said, which just says, hey, if you hit this part of the logic, something's not where we want it to be, retry this transaction. And those are basically the only new operators that you need to learn for STM. The other thing we've done along those lines is you'll find there are STM versions of all the data structures that you know if you work with ZIO. So you're used to promise, ref, semaphore, hubs, queues. Well, there's a T version of every one of those. And they have essentially the same API as the ones that you've already worked with. So it's very easy if you're dealing with any type of problem and you kind of hit a wall where you say, well, I can't solve this concurrency problem with the tools I've got, to just switch to the T version of that thing and you're good to go. It's also been a really big focus on performance, both in ZIO 1.0 and then even more in ZIO 2.0, of essentially creating a specialized runtime for these STM transactions, leveraging a lot of the learnings from the ZIO runtime. And that's allowed this implementation to be dramatically faster than other STM implementations, at least twice as fast in kind of common operations and benchmarks, and more in some cases. And also builds in operators and logic for handling some corner cases that can kind of be gotchas with STM in other cases. So one of the things you may sometimes hear about STM is this idea that it's called like an optimistic concurrency framework, which means we're optimistic in the sense that we're going to do all these things to try to do this transaction. And then at the very end, if we find someone stepped on our shoes and modified one of the things we were working with, we'll retry the whole thing. And one of the problems you can run into there is situations of very high contention where kind of you get stepped on again and again and again, and you have to retry again and again and again. And so the STM runtime actually has special logic built in for it to handle that, where if it observes that occurring, it'll start to prioritize some of these transactions and make sure they get through so that you don't get stuck in that, like this one's called like a retry storm situation. So we're getting the end of our talk here. Let's try to like maybe summarize some of this with a maybe not so simple problem. So this time we've been asked to model a queue of events that are sorted by the time to run. And we want to create a process that takes events from the queue and runs them, but only if it's the appropriate time to run. And so the funny thing we realize if we try to do this with the traditional solution is we actually can't really solve this problem without weakening guarantees in other parts of our system. Because to know if we should run a value at all, we need to take it from the queue. But if this is a mutable, if this is a concurrent queue, then we've got an issue here because we have to take this value from the queue, and it might be that it's not time to run it. So we shouldn't have taken it from the queue at all. But then we've created this inconsistent state where maybe the queue is empty and someone now is going to do something wrong because the queue is empty, even though the queue shouldn't really have been empty because we should never have taken this value because it wasn't time for it to run. And we might think, well, we could poll the queue first and we could look at the first value and see if it's time to run, and then we could take it. But if we're in a concurrent situation, by the time we poll and we get done with that and then we try to take a value, the value we take might not be the one that we poll. So we don't actually have a way to solve this at all without weakening guarantees or making other people do different checks in different parts of our system, which reflects this problem that like we can't actually always do to put everything into one state if some of the state is somewhere else that someone else created. In contrast, here's what the solution looks like with ZIO STM. All we do is we retry if it isn't time to run yet. So this time we're going to have these events that we can think of as having a ZIO effect we want to run and a instant that is when it should be run. And all we'll do is first we'll just use the clock service to get the current time. And then we'll take a value from this queue and we'll see if it's time to run. And if it is, we'll go ahead and we'll run this effect, and otherwise we'll retry. And this retry is going to take care of that logic of if it's not, it's just going to roll this thing back and no one's ever going to observe that we took this value from the queue. And we're going to take this whole thing, we return the ZIO value, so we're going to call flatten to actually run that ZIO value, and we're just going to repeat this whole thing forever. And this is just very naturally going to do all the things we want of like, if there's no value in the queue or if it's not time to run, this is just going to semantically block. It's never going to block a thread. It's never going to busy poll. And it's going to retry when this queue gets updated to have an additional value in it. So this is a problem that not only couldn't we have really solved before, but we can now do in this really elegant way. So in conclusion, I think STM is a tool that a lot of people could be getting a lot more use out of. Hopefully this has been a motivator to do that. And I really want to thank both John and Dayon, who've done a ton of work on pioneering this functionality in ZIO, as well as all the other ZIO contributors and users. and finally, the conference organizer putting this together, and all of you for attending today. So hopefully this was a helpful and educational talk. Thank you so much for your time.